Hi guys, welcome back to another athlete and arithmetic video. Today, I'm going to be your guide to understanding everything about speed, distance and acceleration. Before starting, if you're watching this, please could you subscribe as I don't post very often, but when I do post, they're good videos. Additionally, if you have any topics you want me to discuss which relates to maths and sports, please leave me a comment, as I'd be more than happy to explain them. By the end of this video, you should be able to fully understand stats about speed, distance and acceleration when consuming sports media. To start with, we'll talk about speed. In most sports, this is what we talk about. However, in the sciences, we tend to talk about velocity. The difference is that speed measures distance travelled per second, but velocity measures the distance between the start and the finish per second. This is more commonly known as displacement. You may have heard this in school before. We'll assume we're talking about velocity for the calculations in this video. Now that's covered, let's talk about acceleration. Acceleration is the rate at which velocity changes. For example, if velocity changes from 5 meters per second to 10 meters per second, this will mean your velocity will have changed 5 meters per second in a second. At the end of this then, we say that you have an acceleration of 5 meters per second. Another way we can say this is 5 meters per second squared, which can be written like this or like this. You'll probably just also Mbappe because that acceleration is insane. Something you may have noticed here is how I used meters per second. This is known as the base quantity and is very useful when calculating other aspects such as force. Simple enough? Let's introduce calculus. Let's say someone was accelerating at 2 meters per second squared. Can you model their velocity? Yes, and we do this through integration. All we need to know is that to integrate anything, first increase the power by 1 and then divide the coefficient by the new power. For example, 10x is equal to 10x squared over 2, which is equal to 5x squared. For this example, we'll use t as the variable instead of x, as that will represent time. Going back to the initial acceleration of 2 meters per second squared, we can model this as 2 times t to the power of 0, as t to the power of 0 is equal to 1. This means that when we integrate it, we get 2t to the power of 1 divided by 1, which is equal to 2t. This will be the model for their velocity. A key thing to note is that we represent models for things like this as at and stuff like velocity as vt. Something else we have to add is a constant, as what we've calculated only describes the rate of change, but not the current velocity that they may have at the time. We'll write this down as c. Finally, the model for this velocity is equal to vt is equal to 2t plus c. This says that when we integrate the model for at, we can get vt. We can do this again to vt to get st, which is the model for displacement. And we do this exactly how we got vt from at. Additionally, if we know that the player isn't moving at the start, then we can write c as equal to 0, and therefore just ignore that. So to find st, we have to integrate vt, which is equal to 2t. Doing the same process we did before, we get 2t squared over 2 plus c is equal to st, which is the model for the displacement. Therefore, the final model for displacement is 5t squared plus c, where c is the total distance they've already covered, and t is the variable for how long they'll be moving. Knowing this, let's use an example. Let's say Jeremy Doku is accelerating at 3 meters per second squared. When this model for his acceleration is integrated, we get vt equal to 3t plus c, which is his starting velocity. This would make his distance covered equal to 3t squared over 2 plus c, assuming his starting velocity is 0. If his starting velocity wasn't 0, we'd have to integrate this too, as c again can be written as c times t to the power of 0. If this was true, then his distance function would be equal to 3t squared over 2 plus ct plus c. This is a mouthful, and there's a contradiction in it, which is that the c's don't represent the same thing, as the first c is starting velocity, but the second c is distance already travelled. We can represent this by having the first c written as c subscript 1, and the second equal to c subscript 2. If we wanted to use this distance model to find what his distance travelled is equal to, we'd have to know both c's. So for now, let's just say they're equal to 0. This would mean his distance model is equal to 3t squared over 2. Saying that his total time travelled like this is 3 seconds, this would make his distance equal to 3 times 3 squared over 2, which is equal to 27 over 2, or 13.5. This represents his distance travelled as 13.5 meters. There's only one more thing for us to learn about, which is the reverse of this process called differentiation. This is where we go up, like from st to vt, instead of from vt to st. For example, if someone's displacement can be modelled by 6t squared plus 5t, we'll start by separating the two terms and applying a general formula like we did before. The general formula is that a differentiated function in the form of ax to the power of b is equal to bax to the power of b minus 1. So for 6t squared, where 6 is equal to a, t is equal to x, and 2 is equal to b, we get 2 times 6 times t to the power of 1, which is equal to 12t. For 5t, we get 5 times 1 times t to the power of 0, which is equal to 5. So in total, his dv over dt, which is velocity with respect to time, is equal to 12t plus 5. Again, we can use this to get acceleration, in which we get 12 times 1 times t to the power of 0, which is equal to 12, and 0 times 5 times t to the power of minus 1, which is equal to 0. So, acceleration with respect to time is 12. That means that if Cole Palmer's velocity can be mapped as 12t, his acceleration can be mapped as 12, in which his velocity will constantly be increasing by 12 meters per second. A new case though, is that let's say his displacement is equal to 16t. This would make his velocity equal to 16. However, if we differentiate this again, we get acceleration which is equal to 0. This means that he is constantly moving at the same velocity, and he is not getting faster or slower. The final thing you need to know to understand stats around sports media is how to translate between kilometers per hour and meters per second. This is done as by rewriting kilometers per hour is equal to 1,000 meters per 60 times 60 seconds. This means we can multiply kilometers per hour by 5 over 18 to get meters per second. And that's it. Now you'll be fully literate when looking at sports media and understanding stats around velocity, acceleration, and distance. Again, if you enjoyed this video, then please hit the like button. Let me know if it's good. And if you guys have any other ideas, again, let me know in the comments. Bye guys.